papers program for this session. Each one, we have 20 minutes in total for the presentation, but the presenters will have about 16 minutes for making the presentation, and then 4 minutes for questions. Okay, we will advise you, all the presenters, when you have about 3 minutes left for your presentation. So we start with the first one, and the first one, the authors are Rafaida Nesat, Michael Jeffal, Kalim Kakacha, Adel Benjerat, and Abdelhamid Benhaya. And the title of this talk is Electrical and Optical Characterization of Sputtered and Annealed Tin Oxide Silver Structures for TCO applications. So please, I don't know who will be the presenter, but please initiate your presentation.
So greetings, everyone. It is a pleasure and an honor to present our work titled Electron.
Please continue with your presentation.
Okay, thank you. So our work is titled Electrical, Optical, and Optical Characterization of Sputtered and Annealed Zinc Oxide Silver Structures for TCO applications. First things first, let me guide you through the overview of this presentation, where I'll begin with an introduction to TCOs and the motivation and aim of this work. We'll move to the experimental procedure used to deposit and characterize the films. Afterwards, we'll discuss the main findings, followed by concluded remarks and future perspectives. So transparent conductive oxides, or also known as TCOs, are essential in many optoelectronic applications, such as solar cells, flat panel displays, flexible electronics, etc. Among them, the well-known material indium tin oxide has always been the standard for decades for the industry because it exhibits excellent electrical conductivity as well as high optical transparency. However, it is worthy to mention that indium tin oxide faces numerous challenges such as high costs and the limited availability of indium, and the restriction of flexibility due to the mechanical brittlness of indium as well. Besides the environmental concerns, so how can we address these issues? So a lot of researchers have turned to zinc oxide because, for instance, it is low cost, it is abundant, and a non-toxic alternative. But unfortunately, also zinc oxide suffers from a drawback, which is the relatively high resistivity. However, a very promising strategy came to light in order to overcome this limitation, and it is to combine the zinc oxide with a thin metallic layer such as silver. Now, silver improves the electrical conductivity and introduces plasmonic effects, which can also enhance the optical performance. And in this work, we investigate the zinc oxide silver bilayers and analyze how annealing as a post-deposition technique at 400 degrees influences their electrical and optical properties. So the bilayers were essentially deposited via radio frequency magnetron sputtering using a Moorfield Minilab 060 system. and the glass substrates were cleaned ultrasonically in acetone, isopropanol, and deionized water before deposition to ensure the substrates were clean. The zinc layer was then deposited to a thickness of 100 nanometers um, under a 120 watt radio frequency power with a gas mixture of argon and oxygen with the ratio of 66% to 33% respectively. Afterwards, the silver layer was deposited to a thickness of 8 nanometers in a pure argon atmosphere. After deposition, as depicted in these illustrations, went through thermal annealing at 400 degrees for 60 minutes in order to induce the formation of silver nanoparticles, which play the key role here in modifying the optical and electrical behavior. And for the characterization, we have used the Filmatrix F10 RTU visible spectrophotometer for optical measurements and an HMS 5500 Hall system for electrical measurements. So let's move on to our main findings, starting off first with the optical properties. As we can observe in the transmittance spectra, the commercial indium tin oxide maintains high transparency around 80% across the visible to near infrared range as expected. In contrast, the unannealed zinc oxide thin film exhibits a strong surface plasmon resonance dip near around 550 nanometers with a minimum transmittance of about 48%. On the other hand, the annealed V layer shows that the surface plasmon resonance becomes broader and weaker, and the minimum shifts to about 520 nanometers. Besides, the overall transparency has improved to approximately 75%, which indicates that the silver nanoparticles have reorganized. As for the absorbance spectra, we can also observe the complementary behavior where the unannealed thin film shows a visible absorbance of approximately 30% at 550 nanometers, and the annealed film shows a lower blue shifted peak of approximately 20% at 520 nanometers. So these results emphasize that annealing has definitely led to smaller and more uniformly distributed nanoparticles that enhance the optical clarity. So if we look at the electrical measurements, we can see very similar trends in which annealing enhances the carrier mobility, but slightly increases the sheet resistance because of the transformation of the continuous silver layer to discrete nanoparticles. So for comparison, pure indium tin oxide, of course, shows the best conductivity with a sheet resistance of 16.8, while the unannealed V layer has a higher sheet resistance of 23 and moderate conductivity. And for the annealed zinc oxide silver thin film, the resistance increased to 37, but transparency and mobility have improved significantly. So these findings demonstrate that annealing effectively balances the optical and electrical performance and allows us to modify these properties. Because, for instance, you can see that the overall, the FOM figure of merit improves to 2.32 times 10 to the power of minus 2, close to that of commercial indium tin oxide. So to summarize, here are the main takeaways from this work. Annealing has proved to be an effective but simple method to tune the optoelectronic properties of zinc oxide B layers. Besides, the whole process led to enhanced transparency, high carrier mobility, and an overall balanced performance that is comparable to indium tin oxide. This study also highlights the potential of zinc oxide bilayers as low-cost and environmentally friendly alternative, and they could also be promising for applications that require flexibility and scalability. For future work, we do plan to expand this research into several directions. For instance, we'll include X-ray diffraction and scanning electron microscopy to provide an in-depth analysis of the relationship of nanoparticle morphology and film performance. We will also explore different annealing temperatures and even possibly silver layer thicknesses to fine-tune the transparency and conductivity as well. We also want to integrate the zinc oxide silver into solar cells and UV photodetectors to assess real device performance. And last but not least, we plan to deposit test deposition on flexible PET substrates to evaluate the potential of these films for flexible or wearable electronics. Thank you very much for your attention.
Thank you for your presentation. Please activate your camera so that we can see your face when you answer the questions. And now we have time for questions. I don't know if you have any question.
I don't know if you can hear me. I have one question. You have given the value of a sheet resistance. Do you have the thickness for this each of the deposited films? Because sheet resistance is a relative number. So do you have the thickness for each one?
Sorry, can you repeat the last sentence?
No hay micrófono.
Está muy bajito.
Aquí lo tienen. Yes, I am asking regarding the value of sheet resistance you gave. So you did, for example, the amount of a concentration, but do you have a resistivity or a conductivity of the material you deposited, or the sheet resistance related thickness of each material?
I'm not sure if I understand the question. I'm sorry.
Okay, you are giving a value of a sheet resistance.
Yes.
Okay. Okay. So what is the thickness of each material?
So the zinc oxide has a thickness of 100 nanometers. Oh, are you asking for the indium tin oxide thickness?
Yes, for example, or
Yes.
previous for annealed or not annealed samples.
Yeah, both were deposited for the thickness of 108 with silver. So zinc oxide has the thickness of 100 nanometers, and the silver has the thickness of 8 nanometers.
Okay.
So combined, it's 100.
And in case of ITO, what is the thickness?
Yeah, so we use the reference, and the thickness is a bit ultra thin. It's 270 nanometers, around that. So it's a reference. We use the reference for comparison.
Okay, I think it's very important to mention the thickness of the layers.
Yeah.
Okay. Okay, thank you.
Thank you.
I will have. You say in your conclusions that you have similar values for the figure of merit, but the properties of your films are not good enough, since they absorb in the region where this kind of films can be applied to solar cells. So you need to improve the transmittance in the visible region for applying them to solar cells. So I would like to know how you are planning to improve the properties so that you can apply them to solar cells.
We can fine tune it to, we can use the SPR in order to increase, for example, the absorbance to use it for solar cells.
No, you need to decrease the absorbance of the films so that you have a bigger transmittance for solar cells applications. If you show your UV-Vis spectrum is
Sorry?
spectra, can you show your spectra?
Wait. Absorbance? This one?
Absorbance and then transmittance.
Yeah.
Oh, transmittance. Okay.
And you see that in the visible region, you have a very small transmittance compared with the ITO.
Yeah.
And even though you have similar average values, you don't have the adequate properties for applying them to solar cells.
Yeah, true, but
Because you have a high absorption in the UV visible region.
yes,
So
I
you
understand.
need to do something in order to improve the properties so that you have similar transmittance in the whole wavelength range as the ITO.
Yes, I understand.
Okay.
Sorry, but I have to think about it.
Okay. Don't worry. Think about it. And
Yes.
now we can proceed to the second presentation. Thank you for your presentation.
Thank
Please.
you for your time.
The second presentation this afternoon is going to be presented by Tarek, the GOAT, and the authors are Tarek and Abdelhak Mauricio.
Yes, I'm here.
Okay. Thank you. The title.
Thank you, sir.
Okay, the title of the talk is Boosting Short Circuit Current in Perovskite Solar Cells through Gold Nanoparticle Incorporation. So please initiate.
Yes. I don't hear you, sir. Can you hear me?
Yeah, please, can you start your presentation?
I will start the presentation on my desktop. Can you see my desktop?
No, not yet.
Not yet. Okay. How to share my desktop from?
Yeah, you have to display it in your computer.
It's playing on my computer.
Yeah.
But can you see my PowerPoint presentation?
No, we cannot see. Do you have it ready in your computer?
What?
Do you have it ready in your computer?
I cannot find the button which can share my screen on your website.
¿Tú no la tienes aquí? Okay, we will look for it here.
What about now?
¿La tienes? No. Okay. Can you send it by email?
I have sent it.
Yeah,
the
yeah.
two
You
papers.
have sent it, but we don't know where. So send it again.
Okay, okay, I will send it. Can you see my screen now?
No. Okay. It seems. No.
Not yet.
No, not yet. Yeah.
Sí, sí, eso lo
Ah, okay. Okay. Now we can see. Please enhance the image.
Okay, I will enhance it. Okay. How about now?
Okay. Now it is okay. Initiate.
So, good afternoon, everybody. I would like to commence my presentation by expressing my heartfelt gratitude to the esteemed jury presented and members. I am delighted to share with you main result of my research titled Boosting Short Circuit Current in Perovskite Solar Cell through Gold Nanoparticle Incorporation. This research was carried out under the auspice of the AEL laboratory within the Department of Electronics at the University of Patna II. The structure of the presentation is outlined as follows. We will commence by an introduction. Following that, we will present the device and the modeling methodology. Next, we will discuss the results, data set description, and the deep learning analysis. To conclude, we will summarize this presentation by offering some insights
Okay, are you there, Mr. Maucha? Pues no, ¿verdad?